Okay, here we're going to go over how to solve a kinematics problem. And we're going to do this by using a specific example. And in this example, we have a sports car that will accelerate from rest up to its maximum speed. It'll do that at the rate of 6 meters per second squared over a distance of 400 meters. At that point, after it's moved the 400 meters, the driver takes her foot off the gas pedal and lets the car coast to rest. And we're told that takes a total of 5 minutes to happen. Now, we will assume this acceleration right here is constant over the first 400 meters. We will also assume during this 5 minutes, it will slow down at a steady rate. Now, that's not technically true because it'll be slowing down under the influence of air resistance, which will provide a variable force and produce a variable acceleration. We will solve this problem, but that does involve a little more calculations. So at this point, we're going to simplify it by assuming a constant acceleration. Given that, what we want to find is the maximum speed the car reaches, how far it goes from beginning to end, and then we're going to draw graphs of position, velocity, and acceleration as functions of time. To do all of this, first step is to organize all the information in the form of a table. That table will have rows for the various kinematic variables, time, position, velocity, and acceleration, and the columns will be different points in the object's motion. In this case, it'll be the start, when the car is at rest, the middle point, when the car is at its maximum speed, and the end, when the car again comes to rest. So what we're going to do is take all of these elements in the table and fill them in with the quantities we're given in the problem. Now, almost all the time, we can assume that we can set t equal to 0 at the beginning of the problem, unless it specifies otherwise. We can also, generally speaking, put the object at the origin at the beginning of the problem. So we'll define x equals 0 and t equal to 0 to be the start. We are told at this point the car is at rest, so v equals 0. The middle point, we're told the car is 400 meters away from where it started. We're told at this point it's at its maximum speed, because after this point it's slowing down. We don't know when this occurs, so we'll simply call that t equals unknown. Then at the end, we know this is 5 minutes after the middle point, so we add 5 minutes to t. That's when the car again comes to rest. We don't know where that is, but it's going to be some unknown distance d beyond the 400 meters. So that's where the car comes to rest again. In terms of accelerations, we know from start to middle, it'll be accelerating at a constant rate of 6 meters per second squared. And during the second half, we're going to assume this acceleration is constant, but we don't know what it is. So this now fills out the table, so we know the values for the time, the position, the velocity, acceleration at each of the points of motion of the object. Then we just need to say, okay, which one of these quantities do we actually need to compute values for? Well, to answer part A, we simply want to find the velocity at the middle point. That's explicitly what it's asking for. Part B is explicitly asking for the total distance traveled. To do that, we have to find how far the car goes while it stops and add 400 meters. That'll answer part B. To answer part C, we do in fact need to fill in all the other variables so we can complete all the graphs. So we will need to find this time, and we will need to find this acceleration. Those are what we need to calculate. Now, this is the information. How are all these variables related? Well, so long as we can assume constant acceleration, they are related by these 4 equations that we have already derived. For each part of the problem, what we need to figure out is which one of these equations is the easiest way to find an unknown given known values. So what we're going to first do is consider part A. Part A, here we're asked to find the maximum velocity. So what I want you to do is figure out which one of these 4 equations do you think is best to solve that particular problem. A little question box will open up for multiple choice, and I want you to pick which one of those equations, and do so right now. As soon as you do so, the video will start up again, and we'll go over solving the problem. Okay, now that you've picked an equation, my suggestion is we should use equation 3. And the reason is equation 3 is the only one that does not have time in it, and we don't know the time during this part of the motion. It also includes all the things we know and the one thing we don't know. It includes the initial velocity, we know the acceleration, we know how far the object has traveled, and what we wish to find is the final velocity, and they're all in this equation. This number we know, we're starting from rest. We know the acceleration, 6 meters per second squared. We know the distance traveled, it's 400 meters, and the only other quantity in the equation is exactly what we're looking for. That final velocity will be the maximum velocity. So we plug those numbers in and solve for the final velocity, and we get 69.28 meters per second. However, we only know everything to 2 sig figs. That's the acceleration right here. The 400 we can assume is known to at least 2 digits. Hopefully the 4 and the 0 will be significant. And therefore we round this off to 69 meters per second. And that's the answer to part A. Now, part B. Here we are looking for the total distance traveled. In particular, what we need to do is find the distance traveled while the car was slowing down. So again, what I want you to do is look at these 4 equations and figure out which one of those 4 should we use to solve part B. And again, a little multiple choice will open up, and I want you to pick which one of those 4 equations. Okay, hopefully you picked one. The one I would suggest using is actually the last one, equation 4. And the reason is that equation 4 is the only one that does not include acceleration. And at this point in the motion, we don't know the acceleration. But we do know the initial velocity. That's the velocity that it had at the beginning of this interval, which is your 69 meters per second. It's going to come to rest, so we know the final velocity. And we know the time is 5 minutes, so we know the time. And what we wish to find out is how far did it go, which is delta x. So these are the quantities that we know. This is the one quantity we don't know, and it's the only unknown in the equation, so we can solve for D. Plugging the numbers in and solving, we get 10,350 meters, or about 10.4 kilometers. Now, technically, we should round that down to just 10,000, because that's 2 sig figs. But here, I would avoid that only because that's a large number to round down. And then the 400 meters we start out with, when we add to it, would also not change the number and would suggest we only go about 10 kilometers. Formally, that is correct, but when you're dealing with numbers like that, I would argue we should not round down quite so much, because we're probably going to go a little bit closer to 11 kilometers or 10.8 kilometers. That's a judgment call. I would include the answer to be 10.8. But just to make sure whenever you're doing a problem like this that you do know how to do the math correctly, always write down the answer, then write down your rounded value so people can clearly see what you're doing. Okay, so that answers part B, so we're going 10.8 kilometers from beginning to end. Part C was drawing a bunch of graphs, and to draw the graphs we had to find the remaining variable, the time, and the second acceleration. To do both of those, I would suggest we just use equation 2 because that's the simplest and easiest way to get those two. Because in the first case, we're asking how long does it take to go from 0 to 69 meters per second given an acceleration of 6. And the second case, we're simply asking how long does it take to go from 69. What is the acceleration when you're going from 69 to 0 in 5 minutes? And that gives us the acceleration of minus 0.23 and a time of 11.5 seconds. Given all that, we can now draw all the graphs. First graph is very simple. It's the acceleration graph because it's constant. And we have a constant acceleration of 6 for the first period and a constant acceleration of minus 0.23 meters per second squared. And the graph is just 2 straight horizontal lines. Question, however, is what is the total area under this graph and what does it mean? And the little box will open up and I want you to write a short description as to what the area means and what the value for that area is. Well, the total area has to be 0 because the total area represents the change in velocity of the object. And the object starts at 0 and ends at 0, so its velocity does not change. So therefore, the total area under the curve has to be 0. The area under this part of the graph right here, the positive area, will be the speed gain. That'll be plus 69. The area under this long, narrow stretch under the axis will be minus 69 because that's slowing down and coming again to rest. So the total area will be 0. Now, given these two accelerations, we can now draw the velocity graph. Here we have it accelerating at a constant rate to the maximum speed, which is 69, and this is the slow deceleration back down to 0. And next question, of course, is what does the area right here under this graph mean? Again, a little question will pop up, and I want you to tell me what that area means. Well, that area, of course, will be the total distance traveled. In this case, it'll be the 10.8 kilometers. The area under this part of the triangle right here is the 400 meters it does while accelerating, and the area under this large triangle will be the 10.4 kilometers while it is slowing down, and the total area will be the total distance traveled. Once we have these two velocity graphs, we can then sketch the position graph. Now note the position graph is always positive because it is always moving forward. This little region right here, up to technically 11.5 seconds, is a parabolic curve opened up. That's the accelerating region. And this region right here is it's slowing down and coming to rest. Formally, right here, the velocity should be 0. So the tangent to the curve should be horizontal. And right here, the velocity is 0. So the tangent to the curve should be 0. And this distance right here is the final 10.8 kilometers. And again, the question would be, what does the area under this curve represent? So that's this area right here. What does that represent? Again, a question will open up, and I want you to tell me, what does the area under this curve mean? Well, hopefully you figured out the area under this curve means absolutely nothing. That has no meaning, no significance whatsoever. And we can see that because all the other areas we're multiplying a time by a rate. You multiply velocity by time, you get a distance. You multiply acceleration by time, you get a velocity. But you multiply position by time, you don't get anything that means anything. If I told you I want you to give me 12 second meters, you would understandably look perplexed because 12 second meters means nothing. And that's what the area under this curve would mean. It would be a distance times a time, and that has no meaning. So in this case, the slope has a meaning, but the area does not. And that wraps up the problem.